Let's talk about the optical absorption in a simplified way. If we draw the conduction band and valence band in semiconductors with a band gap Eg, so far what we were considering is that when light is incident with h nu greater than Eg, we get direct excitation of electrons from the valence band into the conduction band, giving rise to free electrons and free holes. The other types of absorption that I mentioned, impurity absorption, can be depicted in the same diagram as follows. We know that there are donor levels which are just below the conduction band, and there are positively charged donor levels and negatively charged acceptor levels just above the valence band. So, just before the onset of direct band-to-band transitions, one can have absorption from the valence band to a donor level, or we can have absorption from the acceptor levels to the conduction band. So, as depicted in this diagram, we have the fundamental absorption here, but just before the fundamental absorption, we can have weaker absorptions here or here due to impurity transitions. Further, one at very low temperatures, when electrons are when the donor levels are filled with electrons, then if the incoming radiation h nu has energy greater than Ec minus Ed, which is typically a few milli-electron volts, one can get absorption. This is also a type of impurity absorption. Similarly, you can get absorption by excitation of electrons from the valence band into the acceptor levels, giving rise to free holes in this case and free electrons in this case. These absorptions are at long wavelengths because, as we know, if Ed is of the order of, say, 10 MeV or 0.01 electron volts, then lambda is 1.24 by 0.01 or 124 microns. Similarly, if the acceptor energies are of the order of, say, 50 MeV, then this is equal to 0.05 electron volts, then absorption starts at 25 microns. So these are in the infrared. These are shown in this picture as impurity absorption here in the range of 10 to the power minus 2 electron volts, right? So these are also electronic transitions. These are electronic transitions, whereas the Rastral is due to phonon absorption, which I will explain later on. And later I'll discuss magnetoabsorption is due to the application of magnetic field, which can split up these levels and as a result one can get absorption between these levels and the bands or at longer wavelengths. Now let us come to discuss fundamental optical absorption. Between the bands, first for a direct gap and then for the indirect gap semiconductor. Let's take the case of a direct gap semiconductor in which you have the minimum of the conduction band and the valence and the maximum of the valence band at the same value of k. Photon with energy comes in, gives rise to excitation of electrons, and obviously we have to have energy conservation and momentum conservation. The energy conservation law requires that initially the energy of the electron in the initial state plus h nu of the photon must be equal to the energy of the electron in the final state plus minus any lattice vibrations of phonons that may or may not be excited. The momentum conservation laws always have to be satisfied, and this implies that the momentum of the electron h cross ki plus the momentum of the phonon must be equal to h cross k f, the momentum of the electron in the final state, plus h cross Have I made a mistake here? Yes, this is obviously the momentum of the photon. So the initial momentum is that of the electron in the initial state plus h cross k photon must be equal to h cross kf of the electron in the final state plus h cross k of the phonon.
So, but in direct band semiconductor, phonon takes the role or not?
Yes, the question was that in direct band semiconductors are phonons involved or not. I have written the general expression for both direct and indirect gap semiconductors, and we'll see that in direct gap semiconductors phonons are not involved. Okay, it is only for the indirect gap semiconductors that phonons will be involved. Right. Now let us examine these terms individually. For example, what is h plus k? What is the momentum of the phonon, of the photon? If we just examine that expression, the h plus H cross K photon is nothing but H by lambda photon, and we know that lambda, we are talking about photons typically having wavelengths of the order of a few thousand angstroms. Whereas if we look at the phonon momentum, H cross K phonon is H by A, where A is the lattice parameter, which is of the order of 2 to 5 angstroms. So we see that in this case, H cross K photon is much less, by a factor of about 1,000, than H plus K, the momentum of the phonon. As a result, when we draw transitions due to photons, we say that the transition is direct. The change in momentum due to the photon is extremely small. It is negligible. So if we go back to this expression, we can say that this is negligible compared with H plus K, the momentum of the phonon, and hence the transitions due to photons are considered to be vertical. Remember, the x-axis is 2 pi by A. This is typically in the Brillouin zone. So A being much smaller than lambda, this factor H by A is much larger than this factor. Right. Now, if we go back to calculations of the absorption coefficient, for a direct gap semiconductor, we have an electron at an initial energy EI being excited to a final energy EF, which has the same momentum because the momentum of the photon is negligible. We have energy scale 0 and EG. So we want to calculate the absorption coefficient alpha, which is a function of h nu, which will be proportional to Ni, where Ni is the density of electrons in the initial state, be proportional to PIF transition probability I to F, and NF, which is the density of empty or available final states. Now, NF. Now, in order to calculate the total absorption coefficient, obviously we have to take summations of this, because we can have transitions between states which are just separated by h nu. So the total transition probability will be a constant, and summation of such transitions separated by energy h nu, which separates the initial state and the final state. Here we will make an approximation. We will assume that at t is equal to 0k, all valence band states are occupied and all conduction band states are empty. At t greater than 0, obviously, we will use the Fermi function. We know that the occupation probability is given by 1 plus E minus EF by KT. But for simplicity, we will assume that all valence band states are occupied and all conduction band states. Pardon? Yeah, right. Right. So let us first consider allowed direct transitions. That means transitions which fulfill the selection rules and the transition probability is finite. We can say that every initial state at EI can give rise to an electron at an energy EF if the difference in energy is given by the energy of the photon. We know in parabolic bands EF minus EG is h squared k squared by twice ME star, and EI is equal to h squared k squared by twice MH star. So using these expressions, we find that h nu minus Eg is h squared k squared by 2 me 1 by me star over 1 by mh star, and we can say that this is a reduced effective mass such that 1 by reduced effective mass 1 by mr star is equal to 1 by me star plus 1 by mh star. So we can write this relation as h nu minus Eg is equal to h squared k squared by twice mr star, where mr is the reduced effective mass. Now we go back and use the density of states expression that we have derived. The number of states having energies between E and E plus dE is nh nu dh nu, that is equal to 8 pi k squared dk over 2 pi cubed, or this is equal to 1 by 2 pi squared h cubed, and here we have the reduced effective mass twice mr star to the power 3 by 2 h nu minus Eg to the power half d we may refer back to the expression already derived. This is the same expression, 1 by 2 pi squared. Where we have replaced this m star by the reduced effective mass m star, mr star, and E is being replaced by h nu minus Eg. Okay. So this is for excitation into the conduction band. Incidentally, there was a mistake here that was not pointed out. This first expression, is it correct? Yes, there is 8 pi cubed here, right? Okay. The important part is that the density of states is proportional to the effective mass. So if you have a low effective mass, the density of states is low, and it goes as e to the power half dE. Right? So you want to depict the density of states Ne as a function of energy. The density of states is 0 in the band gap, and then it increases as e to the power half. And this is of fundamental importance in these calculations of density of states. Now, using this, one can substitute and find that alpha h nu is equal to A star over h nu minus Eg to the power half, where A star is equal to Q squared twice Mr star to the power 3 by 2 over NCH squared Me star. So for direct allowed transitions, we have a very important relation that alpha is going as h nu minus Eg to the power half. So if alpha is equal to A star h nu to the power h nu minus Eg to the power half, alpha squared will be proportional to h nu minus Eg. So if alpha is measured experimentally, one plots alpha squared against h nu minus Eg for different semiconductors, and if one finds that extrapolation of this to the energy axis gives you the band gap of a semiconductor. So this is the test of a direct gap semiconductor, that alpha is proportional to h nu minus Eg to the power half. What about this constant A star? We can evaluate A star from this expression. We can say that for semiconductors with refractive index, say n is equal to 4, if Me, for simplicity, we assume Me star is equal to Mh star is equal to M0, the free electron effective mass, free electron mass, then we find that this constant A star is 2 × 10⁴. So approximately we have, for a direct gap semiconductor, alpha is 2 × 10⁴ h nu minus Eg to the power half centimeter inverse. So for gallium arsenide, one has a band gap of 1.41 eV, and as discussed earlier, since alpha is of the order of 10⁴, if alpha is of the order of 10⁴, then the absorption depth xd is 1 by alpha is of the order of 10⁻⁻⁴ centimeter. This is for a direct gap semiconductor. For an indirect gap semiconductor, like silicon, the band structure is shown like that. So this is energy, this is momentum. In order to get transfer of electrons from the valence band to the conduction band, absorption of photon energies must be followed by either absorption or emission of a phonon, which will, this is emission of a phonon, and this corresponds to absorption of a phonon. So if I draw that, so if this is the photon energy, for the case of emission of a phonon, this energy is Eg plus Ep, where Ep is the phonon energy and this energy is Eg minus Ep. And this momentum is conserved due to phonon participation. So in this case, and this is phonon emission, and this is phonon absorption. So the energy relations are H nu, for the case of emission, H nu E is equal to EF minus EI plus EP, E phonon, and the case of H nu absorption is equal to EF minus EI minus EP. Now we have to again use the density of states expressions. At the initial energy EI is NEI is 1 by 2 pi squared H cubed twice mH star to the power 3 by 2 EI to the power half. And the density of states at EF is NEF is 1 by 2 pi squared H cubed twice ME star 3 by 2, and the energy is EF minus EG to the power half. 2 pi squared, right? And substituting these values of H nu emission and H nu absorption, one can rewrite this as equal to 1 by 2 pi squared H cubed twice ME star to the power 3 by 2 H nu minus EG minus plus EP plus EI to the power half. So the absorption coefficient we know is proportional to NEI into NEF and into probability of interaction with the phonons. This is where indirect gap semiconductors differ from direct gap semiconductors in that phonon absorption or emission is involved. So, what is the probability of interaction with phonons? Probability of phonon interaction is obviously proportional to the number of phonons having the right energy EP, and we know that from Bose-Einstein statistics NP is equal to 1 by e to the power EP over KT minus 1. So if we put this in, the expression of the absorption coefficient for an indirect gap semiconductor comes to a constant F, probability of interaction with phonons, integral EI to the power half H nu minus EG minus plus EP plus EI to the power half DEI. And the integral limits are for all possible energies which with either emission or absorption of the phonons gives you the final energy state of EF. After doing this integration, we find that the final expression for optical absorption with phonon absorption is equal to some constant H nu minus EG plus EP squared over exponential EP over KT minus 1. This is for H nu greater than EG minus EP. Notice that here we have the absorption coefficient is proportional to this energy term squared. For the case of absorption with phonon emission, alpha E H nu will be equal to a constant H nu minus EG minus EP squared over 1 minus exponential minus EP by KT. And this is for H nu greater than EG plus EP, because the energy is a little more, because the energy must be equal to the band gap plus the energy of the phonon which is emitted. Whereas in the other case, we have for phonon absorption, we have this H nu greater than EG minus EP, because the phonon is absorbed from the sample, because the energy is slightly, threshold is slightly less. since if both phonon absorption and phonon emission are possible, then obviously alpha h nu will be equal to alpha absorption plus alpha emission. Now, at low temperatures, phonon density is very small. So there are very few phonons for absorption, therefore alpha A is small, and it's mainly phonon emission that occurs. And as a result, if we plot root of alpha in this case as a function of E, we find that at very low temperatures there's hardly any phonon absorption. At T1 we get a variation like that, and this is the threshold Eg plus Ep, whereas at a higher temperature we will get something like T2 greater than T1, we get the threshold at Eg minus Ep, because absorption is possible, and this is proportional to alpha E, and this is proportional to root alpha A. Summing up in a nutshell, we find that in the case of indirect gap semiconductors, we have alpha proportional to h nu minus Eg minus plus Ep squared, whereas for direct gap semiconductors we have alpha h nu is proportional to h nu minus Eg to the power half. As a result, if we compare gallium arsenide with alpha as a function of energy, for silicon the absorption starts at the edge, increases very slowly, and then this is at the edge of 1 point for an indirect gap semiconductor, whereas for gallium arsenide the edge is at a high energy but increases very rapidly. This is at the edge of 1.42 eV, and we have very rapid increase. So at a slightly higher energy of about 1.5, the absorption coefficient of gallium arsenide could be something like 10 to the power 4, whereas the absorption coefficient of silicon would be something of the order of 10 to the power 2. Any questions?
So suppose an electron is in conduction band. When light falls on that, is there any change of that? It conducts or it goes to a higher level, or any other changes occur?
The question was that if an electron is already in the conduction band and if a photon is incident, can it be excited to a higher level? Well, this is what is known as free carrier absorption. An electron can be excited to a high level, but then it depends upon the conduction band structure. Again, phonons must be involved. Electron can be excited to a high level in the conduction band with the help of phonon participation. And this depends upon the density of electrons. It depends upon the conduction band structure and the phonon densities.
That means in absorption spectrum, we get in absorption spectrum we get the splitting of that level.
No, you get splitting of the levels only if you have magnetic fields applied. If I go back to the original diagram that I showed, okay, right? This is free carrier absorption due to electrons in the conduction band or holes in the valence band. Okay, and this continues. One can say that this continues like that. Okay, and it goes as lambda to the power n. For classical free electrons, this increases as lambda squared. Drude electrons, but in general it goes as lambda to the power n, and this is free carrier absorption. And there's no particular structure. There's no. It goes as lambda squared. There are no specific peaks corresponding to that.